Hello, my name is Louise Daly, and today I'll be discussing how AI and robotics are transforming space exploration. In particular, we'll look at four key research topics: autonomy, human interaction, multi robot coordination, and reinforcement learning. All of these technologies are critical for enabling long term space missions such as planetary exploration and base construction on Mars. Something pretty neat is that the image you see here is one I actually took myself. This is NASA's Valkyrie robot, and Valkyrie is a humanoid robot designed to help build the first human base on Mars. We'll talk more about it later in the presentation, but I think Valkyrie is a great representation of the future of robotics in space, and it's an example of how AI-driven robotics will play a key role in off-world exploration. Now let's take a closer look at why robots in space are so important. Space agencies like NASA and private companies like SpaceX are both working toward establishing a human presence on Mars. However, humans cannot do this alone, and autonomous robots will be essential for constructing infrastructure, transporting materials, and maintaining systems before astronauts even arrive. This image shows a conceptual plan for a Mars base, which could be largely built by robotic systems operating autonomously. But how can robots function on their own in such a harsh and unpredictable environment like Mars? Imagine trying to control a robot on Mars with a 20-minute delay between every command. By the time your instructions arrive, the robot could already be facing a new challenge. When we send robots into deep space or onto another planet, real-time control simply isn't an option. And that's why AI-driven autonomy becomes essential. It allows robots to operate independently, making decisions without waiting for human instructions. And a great example of this is SpaceX's Crew Dragon capsule, which you see here in this image. Unlike earlier spacecraft, which required astronauts to manually dock them to the International Space Station, Crew Dragon uses the advanced AI navigation system to detect the station, align itself, and complete the docking process entirely on its own. This kind of autonomy is critical for future missions, where robots will need to make split-second decisions in these unpredictable environments. One of the key challenges for planetary exploration is that there is no GPS in space. So robots exploring the moon, Mars, or asteroids must rely on alternative navigation methods. Research done by Dr. Vijay Kumar focuses on stereo-visual inertial odometry. Basically, a fancy way of saying it's a technique that allows drones and robots to track their movement using a combination of cameras and inertial sensors. While this research was originally applied to Earth-based autonomous drones, the same principles are being adapted for space exploration. AI-powered navigation systems like these will enable future lunar and Mars rovers, planetary drones, and asteroid landers to map terrain, avoid obstacles, and make real-time adjustments to their flight paths, all without human input. Instead of following pre-programmed routes, these AI-driven robots will sense their surroundings, detect hazards, and automatically navigate unknown environments, making them invaluable for space missions. And robots aren't just exploring space, they're also working alongside astronauts. AI-powered robots are being developed to assist with complex and time-consuming tasks, allowing astronauts to focus on mission-critical operations. These robotic assistants can perform maintenance, operate tools, and even help with scientific research and daily operations aboard space stations and future planetary bases. I mentioned it at the beginning of my presentation, but now I want to circle back to one of the most advanced space robotic systems we have today, and that's NASA's Valkyrie robot. It was specially designed to support future Mars missions. Valkyrie is a humanoid robot capable of handling tools, performing repairs, assisting in scientific research, and by using AI, it can interpret human commands, recognize objects, and work autonomously when needed. Another example is Robonaut 2, which you see here in this photo, which was actually tested on the International Space Station. This robot helped astronauts with routine maintenance, such as cleaning the handrails, organizing the tools, overall just reducing the astronauts' workload. So now we've seen how AI enables individual robots to assist astronauts, but how do we coordinate multiple robots to work together with humans on complex tasks? The CISRU system addresses this challenge by enabling seamless collaboration between astronauts, robots, and when possible, mission control. A major challenge in extraplanetary base construction is going to be ensuring that multiple robots can work efficiently without interfering with one another, or more importantly, putting astronauts at risk. The sister system solves this by using AI-powered coordination, allowing the robots to detect obstacles, reroute paths, and work together in real time. This ensures that things like excavation, material transport, and infrastructure assembly happen smoothly, but most importantly, safely. This diagram illustrates how Sisri integrates AI-driven robotics with astronaut operations. So instead of astronauts manually controlling each robot, AI enables these systems to coordinate tasks autonomously, while the astronauts provide high-level direction and feedback. Robots equipped with autonomous navigation and perception can adjust their actions dynamically to respond to new challenges. One of Sisru's biggest advantages is that these AI-driven robots can do things like prepare landing sites, deploy solar panels, and build habitats long before astronauts arrive, ensuring that essential infrastructure is already in place when humans do finally set foot on Mars. So, we focused on how AI enables robots to assist astronauts and do things like build planetary bases, but AI also plays a crucial role in managing large-scale autonomous systems in space. And a great example of this is Starlink. I'm sure you've heard of it, but Starlink is SpaceX's AI-driven satellite network. Starlink currently consists of, there's thousands of satellites. It currently consists of over 7,000 in orbit, but their goal is to reach 12,000 orbiting satellites by 2026. This image shows Starlink satellites forming a massive multi-satellite constellation. Unlike traditional satellites, which operate independently, Starlink satellites function as a team, using AI-powered coordination. Each satellite continuously adjusts its position to optimize coverage and avoid collisions with space debris, all without human input. There are three main AI-based approaches to multi-robot coordination, and the way these robots, or satellites, interact depends on the task they're designed to accomplish. One approach is called a leader-follower model. This is where one robot acts as the leader and others follow its instructions. This is useful for missions where a convoy of autonomous vehicles need to move across planetary terrain. So think like a rover leading a group of supply robots to a base. Another approach is swarm robotics, which you can probably guess takes its inspiration from nature. Just like ants or bees work together using simple local rules, swarm robots communicate with their neighbors to form self-organizing systems. This method is useful for tasks like search and rescue missions or planetary exploration. This is where small robots can spread out, scan the terrain, and share information with each other to create a real-time map of their surroundings. So instead of relying on a central command, the swarm adapts dynamically, making it highly flexible. And the third approach is distributed AI systems, which is the model Starlink uses. Unlike leader-follower or swarm robotics, distributed AI allows each robot, or in this case, satellite, to make its own decisions while still sharing data across the network. There's no single satellite in charge, but together they adjust their positions and coordinate movements to maintain coverage and avoid collisions. This same method could be applied to future planetary robots, allowing them to explore Mars or the Moon, transport materials, and construct habitats, all while working together autonomously. So now we've looked at different ways AI enables robots to collaborate, but beyond just working together, space robots need to physically organize themselves in efficient ways. AI doesn't just help them cooperate, it determines how they move, align, and structure their formations for different types of missions. Coordinating a team of space robots isn't as simple as assigning tasks. These robots must constantly adjust their movements, maintain communication with each other, and optimize their positioning without human intervention. This is especially important in missions involving multiple satellites, autonomous spacecraft, or planetary robots working across vast distances on the surface. This image here highlights the three major AI formation strategies: trailing, cluster, and constellation formations. Each one is designed for a specific type of mission. So in a trailing formation, shown on the left, robots, or satellites, move in a synchronized path following one another. This is commonly used for mapping and surveillance, allowing for high-resolution planetary scans and large-scale data collection. The middle image shows a cluster formation, where multiple robots stay closer together and share sensor data to improve their precision. This is useful for satellite servicing, asteroid exploration, and coordinated construction projects. This is where precision and real-time data exchange are essential. And here on the right, we see a constellation formation, where satellites spread out to provide maximum coverage for communication, navigation, and Earth observation. This technique is what enables networks like Starlink, ensuring that there's always at least one satellite in range of a target. So, we've seen how AI helps space robots work together efficiently, but what happens when a robot is on its own, much like our Mars rovers, facing an unpredictable landscape with no pre-planned path? In these situations, robots need more than autonomy and coordination. They need to learn and adapt in real time. This is where reinforcement learning comes in. This image illustrates how reinforcement learning works in a planetary exploration context. The rover in the image is navigating through rough terrain, making real-time decisions about the safest and most efficient path. The green path represents a successful, obstacle-free route, while the red zones indicate hazards. And unlike traditional approaches where movement is dictated by a preset of instructions, RL-based rovers continuously refine strategy through trial and error. It will test different routes, receive rewards for successful navigation, and eventually learns to avoid dangerous areas, optimizing its movement over periods of time. Reinforcement learning is already transforming space robotics, and research from the RL STAR platform at Tohoku University demonstrates that reinforcement learning improves autonomy in planetary exploration, allowing robots to make split-second decisions without waiting for commands from Earth. And the armchair research paper that I read further highlights how inverse reinforcement learning, or IRL, enables robots to learn from human actions. Instead of relying solely on self-experimentation, IRL allows robots to observe astronauts, understand their decision-making processes, and adapt the robot's behavior accordingly. This capability is especially important for things involving astronaut-robot collaboration, where robots need to potentially predict human needs and respond proactively. I mentioned the armchair research paper, which explored how robots can learn by observing human actions. But the real breakthrough here isn't just that robots can copy human movements. It's that they can predict what humans will need before they even ask. That's what makes the armchair system so powerful. Because one of the biggest challenges is ensuring that robots can work alongside humans without needing the constant instructions. And the armchair system addresses this by using the inverse reinforcement learning, or IRL, not just to observe, but to anticipate astronaut actions in real time. It allows robots to proactively assist with complex tasks, making them more than just tools. They become true mission partners. And the diagram here illustrates how armchair works. The system first learns from human demonstrations, creating a human prediction model. That allows it to forecast the astronaut's movement. It then applies the MPC-MIP algorithm to calculate the most efficient movement strategy, ensuring that it moves smoothly while avoiding obstacles, but also completes the task efficiently. This means that instead of waiting for direct commands, robots can assist astronauts instinctively, much like a well-trained teammate. And of course, making real-time predictions about human behavior isn't simple. The image on the right represents the advanced algorithm behind Armchair's human prediction system. And while we don't need to go into the exact math, what's important here is that this AI can process environmental and behavioral cues faster than a human could manually program it. This allows robots to dynamically adjust their actions based on the astronaut's needs. And I would like to close with just stating that for as long as humans have looked up at the night sky, we have dreamed of exploring the cosmos. Today, AI is turning that dream into reality. These intelligent systems are not just tools, they're pioneers. They're helping us push beyond the limits of what we once thought was impossible. They will build the foundations of the first human settlements on other planets, guide us through uncharted worlds, and work alongside astronauts as we take our first steps toward a future among the stars. AI-driven robotics will not replace human explorers, but rather amplify our potential, allowing us to go farther, stay longer, and achieve more than ever before. As we stand on the edge of this new era in space exploration, the question is no longer whether AI will shape our future, but how boldly we will embrace it. Thank you.